frequency response of amplifier circuits, or in general frequency response of circuits. How do you calculate frequency response of any circuit? So if you go back to circuit analysis 2, which used to be only circuit analysis, in circuit analysis, towards the end of the course, we discussed the frequency response of the first order filters, RC filter, RL filter, and the second order filters as well, RLC filters. And the main idea behind the frequency response of a circuit is, if you are exciting your circuit with a sinusoidal source, if your input is sinusoid, then of course your circuit may have inductive components, capacitive components. So when you change the frequency of the sinusoid, so instead of changing the magnitude of the input, if you change the frequency of the sinusoidal source, then those inductor and capacitors in the circuit, of course, their behavior is going to change, because remember the reactance of inductor and reactance of capacitor. What is reactance of inductor? XL is equal to j omega L, and reactance of capacitor is XC over 1, XC equals 1 over j omega C. Omega is the angular frequency, which is equal to 2 pi f. F is the cyclic frequency in hertz. So as you will change the frequency of the input source, the reactance of inductor and capacitor is going to change. Now whether that inductance and reactance are specific components that you're using, or if that inductance and reactance are coming from lines, or BJT between the two layers of BJTs or diodes, whatever. There are many types of different inductors and capacitors, capacitance that are present in an electronic circuit, even if you do not put a specific inductor or capacitor in the circuit. So every electronic circuit is frequency dependent. That is, there is a range of frequencies over which that electronic circuit works as you want to make it work, that is, as intended. But outside that frequency range, the circuit does not work as you intend that circuit to work. As you will see in chapter 4, we will study the AC response of the circuit, that is frequency response of the operational amplifier circuits as well. Anyways, coming back to frequency response, so basically the idea is that you are changing the frequency of any circuit, input is sinusoid, and you are observing the output of the circuit as how does it change with response to the change of the frequency. Now remember, when you solve the AC circuits, again go back to circuit analysis, when you were solving the AC circuits with the sinusoidal source at steady state, you were solving as a function of j omega. That is, you are solving in the complex frequency domain. Your every quantity in the circuit was a complex number, which is given by the magnitude and the phase. So input used to have a magnitude and a phase. Of course, inductor, capacitor change from henries and farad to ohms, where ohm is the inductive reactance, j omega L, and ohm is also the capacitive reactance, 1 over j omega C. And the reason we do that is, or one of the main reasons that we do that, is to make our life easy. Instead of solving everything in time domain, we solve in frequency domain. We can observe the frequency relationship, and also we can apply the algebraic rules instead of differential equation to solve any circuit. So going back to, this is one of the circuits that we discussed in circuit analysis, simple RC circuit. And towards the end of the course, when we were discussing filters, so this is basically a low pass filter. So remember, there are 4 different types of filters: a low pass, high pass, band pass, and band stop, or band reject. Low pass is basically it let all the low frequencies up to the cutoff frequency go through the circuit, and it will stop rest of the frequencies above that cutoff frequency. Likewise, high pass, it will stop everything up to the cutoff and let all the frequencies above cutoff pass through it. Band pass, you have a band of frequencies which is allowed to go through the circuit, and rest of the frequencies will be stopped. And band reject is opposite of band pass, where a band of frequencies will be rejected or stopped and would not let go to the output, and rest of the frequencies will go through the output. So when we are discussing the frequency response, the first thing that we do is to write the equation of the output in terms of input in the frequency domain, in the complex frequency domain. That is, we assume that all the components are in the complex frequency domain, and capacitor and inductors are reactants, and everything is given as a complex number in either the rectangular form or the polar form. So when we write the frequency response of this, or write the output in terms of input, basically from this circuit B, so V out, using voltage division, V out equals input times the reactance of capacitor divided by R plus XC, right? Simple voltage division. The only difference is our numbers are complex. Numbers are not real, they are complex. So here's the voltage division that I applied, and of course XC is 1 over j omega C. So I simplified this, and I'm gonna get to this form right here. And most of the time it is written in the form of 1 over 1 plus j omega over omega naught, or omega B, or omega C, whatever you want to call it, where omega B, omega C, omega naught, whatever you're calling it, is the cutoff frequency or the break frequency or the corner frequency, also called 3 decibel frequency. So anytime a circuit is given to you, and these are the first order circuit, because first order means that there is only one reactive components and in the time domain the equation of the circuit can be given with the first order differential equation. So for the first order circuit, also called the single pole circuit, for the first order circuit, the general expression will be given by this equation, and again it depends on the circuit, how your circuit looks like. Based on that, you have to derive the equation of the output to the input, and then you will have to decide how the equation looks like for that circuit, right? But for the circuit that I'm showing you, this is called a single pole circuit. Pole means that you have at the denominator, in the denominator you have only one root. If you have two roots, that's a double pole circuit, one factor, right? So the derivation of this, from the derivation of this circuit, we found that output voltage is equal to 1 over 1 plus j omega over omega B, which omega B is the break frequency or cutoff frequency, and that is equal to 1 over RC from this relationship, right? Because this is 1 over 1 plus j omega RC, so we just take the RC and then put it under j omega, and of course when you put it under j omega, it's just gonna be 1 over RC. It's the same thing. So the break frequency of this circuit is 1 over RC. What is the concept of break frequency, by the way? Break frequency or cutoff frequency is the frequency at which the response, the magnitude response of the circuit, of the filter, becomes 70.7% of the peak value, or 0.707 times the peak value. That is the break or cutoff frequency. Now remember, this is complex quantity. That means each value will have a magnitude as well as phase. So when you are looking at the frequency response, V out j omega will have a magnitude response where you calculate the magnitude of V out j omega, and the phase response where you calculate the phase or angle of V out j omega as the frequency is going to change. Your magnitude will change with the frequency as well as phase will change with the frequency, and we draw two plots separately to show magnitude in one plot and phase in the other plot. Okay, so here I'm explaining how you calculate the magnitude. Of course, this is one thing that I advocate in every class. I request all the students that, guys, you need to have good knowledge of complex number manipulation. most of you discuss complex number in early mathematical classes, whichever classes that you took. Of course, we discuss in circuit analysis, DC circuit, AC, whatever. If you have taken control system, we discuss that. DSP, we discuss that. Complex number is one thing that as an engineer you cannot get rid of. Basically, you will be using those complex number, especially if you're an electrical engineer. So again, I will emphasize on the fact that everyone needs to know how to calculate if a complex number is given to you, either in fractional form or regular, how to calculate the magnitude of the complex number, how to calculate the phase of the complex number, transform from polar form to rectangular form to polar form. Everyone should need to know that. Now, do we need to always use simple calculator or our brain to convert it? No, absolutely not. In MATLAB or in calculators, you can easily manipulate different forms of complex number, polar to rectangular, rectangular to polar. But again, understanding is extremely important, because your calculator is going to do whatever you want it to do. But if you are converting, let's say, from rectangular form to polar form, and if your point complex number is in the second quadrant, that means the angle has to be between 90 degrees and 180 degrees. And most of the calculator, it is possible, they will just give you the point in the fourth quadrant. They're going to give you a negative angle. So it is important for you to realize if your answer is correct or incorrect. So once again, I will request you that before you even proceed to work in this course, go ahead and refresh the complex numbers. Just go online. There must be a bunch of tutorials that you can see. Look at those tutorials, do some practice, and refresh the complex numbers. You can use in MATLAB. There are functions available. We discuss in different classes. Or you can use your calculators. But again, the complex number mathematics is extremely, extremely important. Okay. So I hope everyone is going to do that. I'm not going to go over complex number in this course. This is an advanced course, so it is your responsibility to go over complex numbers, and I hope you will. Otherwise, it's quite possible that if I give you a problem, ask you to evaluate the magnitude of that, it's possible that you will not know and end up evaluating incorrectly and lose your points. So magnitude of this right here. What will be the magnitude of this? Magnitude, if it's given in a fraction, then it's going to be magnitude of numerator divided by magnitude of denominator times the magnitude of whatever is multiplying that quantity. So I have V out. If it is italicized, basically it's the magnitude. V out equals magnitude of numerator, which is 1, divided by magnitude of denominator. Anytime you have a complex number given in the rectangular form, the magnitude is a square plus b square. So that's what we did over here, is square root of a square plus b square. And then the magnitude of input, which is V input. And then the phase, anytime a fractional complex number is given to you, phase of that is going to be arctan of the phase of the numerator minus arctan of the phase of the denominator, plus whatever it is multiplying, the phase of that quantity, right? So the phase is arctan of the phase of numerator. Phase of numerator is 0, and then arctan minus arctan of phase of denominator. Remember, how do you find the phase? Tangent inverse of the complex quantity over real quantity, right? Complex quantity over real quantity, and plus the phase of the input. Once again, if you're confused, study complex numbers, please, especially when complex numbers are given as fractional form. And most of the time, instead of calculating the output voltage in terms of input, we calculate the ratio, because remember, we are dealing with gains. So ratio represent gain. So instead of doing V out separately and calculate in terms of V input, we calculate V out over V input. And we represent that as gain, or what we call transfer function of the circuit. So this thing is called transfer function of the circuit, h of j omega, which is the ratio between V out over V in, and which will be 1 over 1 plus j omega over omega naught. In this example, I'm simply uh, plotting the magnitude response and phase response. I'm using MATLAB. And when you are plotting the response curves, it is always wise, instead of using plot function in MATLAB, use the logarithmic scale x-axis using let me see what is semi-log x, sorry, not this, let me erase this, semi-log x. So instead of using plot function, use semi-log x. Semi-log x f comma magnitude of whatever h, if your magnitude of, if this is the variable in which you're holding the magnitude values. Okay. In MATLAB also, if you don't remember from other classes, or if you never took any class with me where we discussed that, complex number magnitude can be found out using the absolute function. Absolute, if for example if h is your complex number, then absolute of h is going to calculate the magnitude of that complex number, and you can assign it to a variable like, let's say, magnitude of underscore h. And phase of the complex number can also be found using a function called angle of h, but angle of h gives you phase in radians. So to convert into degrees, you multiply that by 180 and divide that by pi. So these two functions come very handy when you are calculating the magnitude and phase of the angle, phase of the complex number. And semi-log x is to change the x-axis into logarithmic scale to see the output results better. What does it do is, it basically, as you can see, it divides each tenfold of frequency into equal scale. So for example, if your low frequencies are active but high frequencies are not active, then it will show you properly that low frequencies are active until this point and then it goes down. But if you don't use semi-log x, if you just use plot function in MATLAB and go up to, let's say, 10 to the power 2, 3, 4, what's going to happen? It's going to compress all the lower frequencies, and your graph is not going to look very nice because it's just going to perhaps look like this, something like this. So you will not get a sense of how the shape is changing at low frequencies. So my advice would be use semi-log x instead of plot when you're plotting the frequency response. Okay, so what we are going to discuss next, actually I'll just create a next video. This video is getting long, so next video we're going to discuss Bode plots.